Hello everybody, so this is part 4 of Sedimentary Structures and Fossils. Let's finish this thing off. Okay, so in terms of fossil types, that's body fossils. Alright, so remember that's the body, that's the carcass, the shell or the skeleton. They come in two main groups. There are unaltered body fossils. So that's where we have the original organism, unaltered. So that's a situation where we have something like amber. The amber encases the insect and the insect's body does not decompose. We have the hard parts, we have the soft parts, nothing happens. So other examples of unaltered fossils are frozen fossils. So if you go to certain parts of northern Russia or places like Alaska, you can actually find frozen mammoth, frozen bison in the tundra, and you can dig them out and you can eat the meat. You also have the process of mummification. So mummification is simply where you are living in an area which typically has dry air. The organism dies, and the dry air essentially removes the moisture from the body, just desiccating it, drying it out. Once again though, what you're left with is the original body. It's just lost the water. The final way you can actually have unaltered remains is through preservation in tar. So you probably all heard of the La Brea tar pits in California. If an organism goes into those tar pits, then the body you get out from them is not going to be the original body. So the muscles, the skin, everything else, that will fall off the carcass. However, the bones will remain in the tar pit at the bottom. And they essentially throw nets in there and they just drag up all this stuff from the bottom of the tar pits. And they have things like mammoth bones, deer bones, saber-toothed cat bones, wolf bones, loads of different stuff. And those bones are unaltered. They are just as they were when the animal went into the tar. Now you've lost the soft part of the body, but you do have the hard part of the body, and it's not been altered in any way. So unaltered remains, they include preservation by amber, freezing, mummification, or tar, because you get the original unaltered body. In terms of altered fossils, well, there are several different types of altered fossils. The first type is recrystallized, then we have replacement, then we have permineralization, carbonization, then we have casts and molds and trace fossils. We already touched on casts and molds and trace fossils, so we're not going to focus too much on those. So recrystallization is simply when the fossil itself, be it the bones or the shell, is made from an unstable mineral. So that mineral might be absolutely great when your organism is making a shell to live on the seafloor. However, as soon as that shell gets incorporated into the sediment and it gets buried and heated up and the pressure gets higher, the material that shell is made from may suddenly find itself unstable. And so what's it going to do? Well, it's simply going to change into a new, more stable mineral. Okay, that's option number one. Typically, when something recrystallizes, the chemical formula remains the same. So that's a situation where we have something like aragonite, which is calcium carbonate. Under increased heat and pressure, will change to calcite, which is calcium carbonate. So the chemical formula hasn't changed, we've just moved the atoms around slightly. Next we have replacement. So replacement is when we have our fossil and the shell or bones get replaced by a completely new mineral. So in the case of a shell, the calcium carbonate gets replaced by something like silica or sulfide minerals. So the original mineral is completely lost. But the new mineral will preserve the morphology of the original fossil. So even though the original fossil's been lost, the new mineral that's replaced it will look exactly like the original fossil. Then we have permineralization, and that's simply when you have a porous material, and the porous material has the spaces in the material get filled up by a new mineral. So that's very common with things like corals and bones and petrified wood. So in the case of petrified wood, there's a lot of space inside the wood, and the very silica-rich waters that pass through the wood deposit silica, so quartz, in the spaces, in the voids in the wood. And so eventually those voids get filled up by silica, and eventually the organic portion of the tree just disappears, but the silica remains. And so essentially what you've done is you've replaced the tree with silica. Finally, we have carbonized films, and carbonized films are the result of taking something like a leaf and sandwiching it between two layers of sediment, typically muddy sediment. So you'll have a layer of muddy sediment, the leaf settles on top, and then another layer of muddy sediment will be deposited over the top. And then that leaf will get exposed to increasing pressure and temperature as the mud gets buried deeper and deeper and deeper. So what exactly happens? Well, as the temperature gets higher and higher and higher, you are baking the leaf. So I'm sure most of us, there may be some of you who are proud of their kitchens, but unfortunately I'm a bit useless. There may be some of us that have cooked a pizza in your oven, and a bit of cheese has fallen off the pizza. It's landed on the bottom of the oven. You think to yourself, I'll clean that up another day. And then you leave it a few rounds of baking in the oven, and it starts to bake harder, and you think, well, if I keep baking it, eventually it's just going to completely disintegrate. And so that piece of cheese gets repeatedly baked again and again and again and again in your oven. And eventually one day you think to yourself, right, I'm going to have to, get that piece of cheese out. And so you take it off the bottom of your oven and you find it's nothing but a lump of carbon. And so what's happened is as you've heated up that piece of cheese again and again and again, you've driven off all the impurities. So you've driven off the water, you've driven off the oils, you've driven off the nitrogen compounds, the sulfur compounds, and all you're left with in the end is just a layer of carbon. And that's exactly what happens with these carbonized fossils. Essentially, you have your leaf, it's trapped between these two layers of sediment, these muds, and the leaf just gets heated up, and the water gets driven off, and the nitrogen compounds get driven off, and the sulfur compounds get driven off, etc. And eventually all that's left behind is just the carbon. And so the fossil itself is this super fine film of carbon, less than a millimeter in thickness. And now this might sound pretty bad because you've lost the original fossil, but the level of detail retained in some of these carbonized fossils is truly spectacular, and we'll see some pictures later on. You'll be your mind will be blown by how good this stuff looks. Okay, so recrystallization. So as discussed, an unstable mineral essentially can change and is typically replaced by a mineral with the same composition. All right, so it's a destructive process, because we can lose some detail of the fossil. So the composition does not change. So if we have a fossil made of aragonite, calcium carbonate, it changes into calcite, calcium carbonate. Replacement is the same thing, but the original minerals are completely lost and they're replaced by a new mineral. So if we just flick to the next slide, so these are all ammonites, and ammonites were very, very common in the Mesozoic, especially during the Jurassic and Cretaceous. Well, actually, I tell a lie, they appear in the Devonian. They're actually common in the Triassic, Jurassic and Cretaceous. So it's probable that ammonites had lots of different shell colors, but here are some relatively unaltered ammonites. So these ammonites are from Russia, and this shell is made from aragonite, sometimes referred to as mother of pearl. So this is kind of what original ammonites would have been made of and maybe would have looked like. Now, as you can see, what we have here are two ammonites that have undergone alteration. Okay, so they've undergone replacement. So the original calcium carbonate has been replaced by, in this case, pyrite, otherwise known as fool's gold. So that's iron sulfide. So that's why the fossil itself looks kind of brassy. Down here, on the other hand, the original calcium carbonate has been replaced by opal, so amorphous quartz. In this instance, though, we have a fossil that's undergone recrystallization. So in this case, the original mother of pearl, so the aragonite, has been replaced by calcite. Aragonite is calcium carbonate, calcite is calcium carbonate. So what's happened is essentially you've lost the beautiful sheen which you had with the original fossil, and instead what you have now is a kind of dull, rather earthy looking fossil. But once again, it's still, you haven't altered the chemical formula of the shell. It's still calcium carbonate, even though you have changed the mineral. In this case, you haven't lost any detail, but sometimes when you do this, sometimes when you recrystallize a fossil, you can lose some of the detail. But you will notice, though, in both of these cases, these replacement fossils have retained the original features of the fossil that they replaced. In terms of permineralization, as discussed, this is simply where pores or voids within bones and organic material get filled in by another mineral. So in this case, you can see a piece of petrified wood. All of the the veins, all of the material within the tree here have been filled in by silica. Silica is of course SiO2, and the organic portion has been lost or replaced by silica as well. Same for these dinosaur bones here. In the case of these dinosaur bones, of course, you may or may not know, bone is a very, very porous subject. Bone is a very, very porous substance. It's got loads of holes in it. And so what happens is the bone goes into the ground during the liquefaction process, fluids pass through the bone, and they fill in the spaces within the bone. Now, at the same time, the material the bone is made from will typically alter as well. So dinosaur bones are formed through a mixture of permineralization and replacement. So these dinosaur bones aren't actually bones, they're technically just pieces of rock that are now shaped like the original dinosaur bones. Now, these are carbonized films. So these are the result of organisms being trapped between two layers of rock and the fossil itself being heated up until you're left with pretty much nothing but the carbon. Now, these fossils themselves, as I said, are extremely thin. They're typically less than a millimeter in thickness, so you can scratch them away very, very easily. Now, I wish I'd put some other photographs in there, but if you take historical geology, you'll see some truly spectacular photographs when we do fossils. Now, molds and casts we've already discussed. Sometimes the fossil, when it's in the sediment, gets destroyed as the rock gets liquefied. This leaves behind a fossil-shaped void, which we refer to as a mold. That can then be filled in later by sediment, which will produce a cast. And the cast will take on the shape of the mold. So, things like these molds here, you can see here of trilobite fossil. That void can then be filled in, and it will leave behind a near perfect cast of the original fossil. So why are fossils really helpful to us? Well, the main power of fossils is using them to date stuff. So if we have a look at this diagram here, you can see here we have the Precambrian, we have the Paleozoic, Mesozoic, Cenozoic, and in this diagram they've selected some key fossils for each of the periods. So Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian, Triassic, Jurassic, Cretaceous, Tertiary, Quaternary. And you'll see here a couple of very common fossils for each of these periods. And so what's helpful about these fossils is, as a geologist, if I walk up to a rock face and I see, something like Recrystallization, this thing down here, well, I know straight away I'm looking at a rock that's Devonian in age. So these things are referred to as index fossils. They're fossils which are very widely distributed. They have a relatively narrow range in time, so we know when they appeared. They didn't appear over a very, very long period of time. They appeared over a very, very limited window. And they are regarded as a characteristic of a given geological formation. So these index fossils are really helpful because, they're all over the place. We know they only occurred for a very, very limited period of geologic time. So that means we can date the rock very, very effectively. And we can use them to essentially characterize certain geologic formations. So, for instance, the appearance of Recrystallization, is a good indicator of Devonian age rocks because it occurred just in the Devonian. So, one of the things we can do with these fossils, these index fossils, we can produce what's called a fossil assemblage. And a fossil assemblage is a group of fossils that occur together in a particular rock unit, so something like a bed or maybe a formation, the things we discussed earlier. So what we can do with these fossil assemblages is we can use them to date layers and correlate layers at different locations, and we're going to discuss how you do that now. So the first thing we need to discuss before we do that is we need to discuss the final principle of relative dating, and that's the principle of faunal succession. And the principle of faunal succession simply states fossils change up section in a systematic and predictable fashion. That means that fossils occur in a set order. So I know what fossils I should expect in Cambrian age rocks. I know what fossils I should expect in Ordovician rocks, in Silurian rocks, Devonian rocks, etc. So if I find the right fossil, that instantly tells me the age of the rocks I'm looking at. And that's it. That's all the principle of faunal succession really says. It says fossils occur in an order which geologists know, so when you go to a rock face and you find a rock that contains that fossil, you know how old it is. Done. Now, in terms of the fossils themselves, some fossils will have huge ranges. So, there's some organisms that appeared in the Ordovician. Okay, so we're talking hundreds of million years ago, and they're still around now. So in terms of dating a piece of rock, that fossil is useless to us, because is that piece of rock 400 million years old? Is it 200 million years old? Or did it form last Tuesday? We don't know, because that fossil has such a huge range. So as geologists, what we really want is we want species that lived for only a very, very short period of time. Because they only live for that very short period of time, when we find them, we know that they essentially could only have occurred during that very short time frame. So we use these fossils to produce what we refer to as range zones. So here are 3 fossils, and you can see these 2 fossils have relatively short, well, these 2 species, should I say, were around for only relatively short periods of time. So therefore, if we find either of these 2 fossils, brilliant, we can date a rock relatively accurately. However, Lingula, on the other hand, pretty useless. It first appears at the start of the Ordovician, and it's still around now. So if I find a rock with Lingula in it, it could have come from the Ordovician, the Mississippian, the Jurassic, as I said, last Tuesday. We don't know. So Lingula is not very good. So first of all, we want fossils that help us to define nice small range zones. So the best fossils for producing range zones are, number 1, easily identified. I just want to be able to walk up to the rock and identify it straight away with the minimum of fuss. I also want the organism to readily fossilize, because I want there to be as many fossils of it as there can possibly be. Well, because once again, that means I'm more likely to find it. I also want it to be geographically widespread. I want it to be everywhere. Because let's think about it. If I have a fossil that was only limited to an area between Houston and Dallas, well, that's great if I want to date any rock between Houston and Dallas. But if I want to date a rock in, let's say, Oklahoma City, it's completely useless to me, isn't it? So what I want is a fossil that's really, really widespread. I want it to be everywhere. And the final thing I want is I need that all-important short geologic range. I want it to have just appeared for a very, very limited part of geologic time. I do not want a big range like Lingula. That's not useful to me. So if I look at this diagram here, this is for a whole range of brachiopod fossils from the Ordovician. So if I'm looking at these and I'm thinking to myself, well, which ones would make really, really good fossils for producing a range zone? Well, I want, first of all, the ones that have a short range. Here we go. These 2 would be spectacular options, wouldn't they? Look at them. They're only around for a very, very limited period of time. And if they happen to readily fossilize, be easily identifiable, and be geographically widespread, that would be truly spectacular. So this is the kind of thing that I'm looking for. These fossils are what I really, really want. So when it comes to fossils, we use fossils to produce what are referred to as interval zones. So an interval zone is essentially when we use a specific range of a fossil species to produce essentially a period of the rock record. So essentially we say, right, this fossil first appears here and another fossil appears here. So fossil A appears here, fossil B appears here. So in between the two, that's our interval zone. So by doing this, we've essentially arbitrarily split the rock up, haven't we? So by doing that, by using these fossils, we've said, right, between here and here, this is our interval zone. And so we can use these interval zones to essentially, split up the rock record. And one of the ways we see interval zones is in things like the geologic timescale. So I'm actually just going to do this for a second. Here is the geologic timescale. It's back on my computer's screen. You can see all of these are essentially nothing but range zones. They are based on the first and last appearance of certain key fossils. And that's all they are. And so, sorry, when I'm saying range zones, interval zones. So these are all intervals. Each of these boundaries, as I say, is based on the first and last appearance of certain key fossils. And, that's it. And they're arbitrary. Don't go thinking that geologists, have some kind of special process. No, they're arbitrary. We just chose a fossil to start one, chose a fossil to finish it, and bang, that's the Oxfordonian. Done. So another thing that we can do with fossils, and this is possibly the most powerful thing we can do with fossils, is we can produce what's referred to as a concurrent range zone. So a concurrent range zone requires you to have 3 or more fossils. And what you do is you end up with a situation like this. So this is going to be location A, and this is going to be location B. So at location A, you can see there's a very, very limited portion of the rock record, the top of this limestone here, where I have fossils A, B, C, D, and E, all in the same rock. Okay, as soon as I move outside this range, if I come down this way, fossils B, C, and E disappear. If I move up above it, fossils A and D disappear. So there's only a very, very limited period of Earth history when fossils A, B, C, D, and E could possibly have coexisted. So I've produced a very, very tight range in geologic time. Now that means when I go to any other location, if I find a piece of rock that has fossils A, B, C, D, and E in it together, well, that means this piece of rock here must be the same age as this piece of rock here, even if it's a completely different rock type. As long as it has A, B, C, D, and E in it, it must be the same age. And so these concurrent range zones are super, super helpful in producing what we refer to as time equivalence. And time equivalence is just simply saying this piece of rock here is the same age as this piece of rock here. And that's very, very important when you're trying to link rock together over very, very large distances. So you can use the fossils to do that, when it would be otherwise impossible to try and trace the layer of rock from one side of a continent to the other. So this kind of gives you some idea. So this is an image from Core Lab. So they're a service company. And you can see, so this is a set of essentially stratigraphic columns for different areas for Canada and the United States. So you can see over here we have British Columbia in Canada, Alberta, Saskatchewan, we have Montana, we have, is that Montana? Montana, Manitoba, and North Dakota. Okay, and so what you're seeing is through the use of things like concurrent range zones, they have been able to age date and link up these rocks. They've managed to work out, for instance, that these layers here are the same age as this layer here, so they can link them together. So they can date each layer of rock, work out where it sits in the sequence, then you can essentially produce a stratigraphic column for each of these locations and line them up next to each other. And so that gives you a lot of information about what was going on about this, within this whole swathe of northern and the northern and central northwestern United States and Canada. So you can see, the geologic changes going on in that area. And so, this is extremely helpful, extremely powerful. And eventually you end up with a situation like this. This is where it really, this is what it really comes down to. So imagine if you have a concurrent range zone and you go to every single location that you can find fossils A, B, C, D, and E, and you literally go everywhere you can in North America that has fossils A, B, C, D, and E. Now everywhere you go, those rocks are going to be the same age. And so what you're then doing is you go to all of the locations, every location you can, and in some locations you say, right, rocks that date to the same age as A, B, C, D, and E, all of the rocks in this area, well, they're marine. So they were underwater. All the rocks that date to the same age as A, B, C, D, and E over here, well, they formed in mountainous terrain. So, this area was mountainous or semi-mountainous. All the terrains over here that we see, they date to the same age as rocks, fossils A, B, C, D, and E. They were all from fluvial terrain. So this area here was covered in rivers. And so literally all you do is you split up the areas based on what environment it was. So eventually you end up drawing a big area over here and you say, right, this area was mountainous, this area was marine, and this area was fluvial. And all of a sudden you've produced essentially a paleogeographic map of North America, haven't you? And so this is how we know what was going on in North America essentially over extended periods of time. We can draw these maps all the way back to accurately to pretty much the Cambrian. And so we know what was going on with, when it comes to the surface of North America, was it covered in water? Was it above sea level? Was it mountainous? Was it, fluvial? Was it desert plains? We have all this information in the rock record. And all we have to do is just make sure we are looking at rocks which are the same age. Because as long as we go to all these locations and we look at rocks which are the same age, we can say, right, at this period of Earth's history, this is what North America looked like. And that's the power. All right. And that's it, everyone. So that was the end of sedimentary structures and fossils. I hope you enjoyed it. So we're going to end here. Don't forget to write down that code word and have a good day.